So I will give people another minute or so to join because we still have people in the waiting room. Okay, so welcome everybody to today's graduate seminar in engineering and technology management. And again, this is under the overarching theme of sensors to decisions, weaving the computational fabric. And I'm super happy that we are joined by Alexander Hunt today, who is a assistant professor in mechanical materials engineering here at Portland State. He has a PhD from Case Western in biologically inspired robotics. And his topic is brilliant bodies, weaving the computational fabric from sensors to action. And Alex just told us before this started that he does a lot of modeling and that he collaborates with biologists trying to understand how animals behave neurologically and to convey some of these things into the design of robotic systems. So this should be a super exciting and very interesting talk. So I'm really happy that he's here. Thank you, Alex, and the floor is yours.
All right, thank you. I'm excited to be speaking with you all today. This is a kind of a new talk for me, kind of a high-level view of my research and some research of my collaborators. And I will apologize ahead of time if we get interrupted by my son. I am at home with just him right now, so hopefully he won't walk through the door, but if that happens, we'll have to go with it. So yeah, I'm here to talk to you about weaving the computational fabric from sensors to action in brilliant bodies. So I know we have kind of a brilliant cities kind of overarching theme, but I'm actually gonna look more at animals and show you more about how the body is organized, the nervous system is organized, and how it works. So where am I positioned in this stack from sensors to decision? Well, I model the entire stack in animal locomotion. So not just looking at one of these different aspects, but actually looking at kind of the whole system together and trying to understand how the system works in animals and coming up with kind of more understandable ideas of control, which I'll kind of point to throughout the presentation here. So here is a great video. So yeah, how does the brain control the body? That's the big overarching question that I am looking at. And we see that the body is capable of doing very complex, highly adaptive maneuvering. And in order to do all of this, how's have this on repeat. It has to take in lots of sensory information from all over the body, coordinate decisions on where to go, what to do, coordinate all sorts of different things, be very adaptive and responsive. And right, we know that animals, humans, we're all quite amazing at our capabilities. I don't know. I kind of want to make this a little bit interactive. I don't know if we can unmute people. Probably people raise hands. So I want to ask the question to you all. How do you think your brain controls your body? Are there any thoughts? So if we take the example of you going to your refrigerator to get something to eat, how does that work? More chat. We've got electrical signals. So electrical signals throughout your body. That is correct. So the nervous system works using electrical signals to communicate throughout, and this helps. Any other thoughts? What do they have to communicate to? I don't know if I can control unmuting.
The nervous system?
With the nervous system?
Mm-hmm.
Yeah. So what does the nervous system do?
It provides passage from the brain to the body.
Mm-hmm. We've got another comment in the chat that you have to activate the muscles to move your body, right? So, yeah, any other thoughts? Electrical signals passing through neurons. How does the body decide which neurons to pass electrical signals through? So these are all kind of the questions, right? So first, the body needs to decide, right, what to do. And then you have to activate your muscles, and you need to do that in a coordinated way, right? So I need to activate the right muscles to push away from my desk in my arms, and then orient my body, activate the right muscles in my legs, pick up my right leg, pick up my left leg, right leg, right? You have to do everything in order, do it properly in timing, open a door. Some other things that you might not even be thinking about, you have to continue breathing while you're doing this. You need to continue to pump blood throughout your body. You have to get the right amount of blood to all your muscles in order to get them the nutrients they need to create energy to contract. And right, and you have to contract all your muscles at the exact right time. Potentially you have to walk around objects, see objects, recognize them, walk around it, change how you're walking, walk downstairs, all these lots of complicated things going on inside your nervous system for what might seem like a very simple task. So what's going on in the nervous system is it's not really a stack. And I would say it is much more a computational fabric. So, and I'll go through this all a little bit more, but, and in this fabric, right, we have one brain, and we are trying to control greater than 650 muscles, right? So there is lots of coordination going on, lots of decision making, lots of stuff. So let's break down our fabric a little bit more. So at the bottom, we've got our muscles. Our muscles are the actuators that move our body around and allow us to interact with the environment. Above the muscles, we have kind of local circuits. So these are neural circuits in your spinal cord, and these control the muscles on kind of a low level, basic level way. So they coordinate which muscles are activated. They do a little bit of timing control as well. We've got sensory feedback. So you've got sensory feedback from your muscles, from touch sensors like in your skin, sensory feedback from your eyes. You also have your inner ear, which kind of helps you monitor balance. Lots of different sensory systems in your body that are coordinated together. And most of these come into your local circuits, where most of your sensory feedback goes directly in. Then above all of this is the brain. And the brain is primarily used to select tasks and modulate the behavior of the local circuits. So let's kind of focus all of this on kind of a specific direction to help us understand more about what these different areas are doing. So let's focus on the simple task of walking. Here you see some X-ray videos of one of my collaborators in Germany, Martin Fischer, and they take these amazing high-speed X-ray videos of different animals walking. Here we have a rat walking. It's walking over just kind of a regular treadmill. And so let's kind of take this idea of walking and start to look at what all these 4 different areas are doing in the process here. So let's start talking about the muscles. Muscles are both awesome and a pain. So here we see kind of a cartoon diagram of all the muscles in a rat leg. And some of the awesome things, but difficult things about these muscles are that many muscles can actuate the same joint, and also many muscles can actuate multiple joints at a time, right? So you don't just have a single muscle that makes your arm close, elbow close, and a single muscle that makes it open, right? So biceps, we've actually got 2 of them there. Triceps, we've got 3 out there. And then we've also got more complex actions going on further down our arm. Similar types of ideas in our legs. We have muscles that cross both our hip and knee, like our hamstring muscles. And one of our quad muscles also does that. And so what this does is it enables specialization towards functional behavior, like picking up an entire leg. So you could use, even though you have like kind of 3 main joints in your leg, you could just use 2 muscles to pick up your entire leg because you have muscles that cross multiple joints. And so you can kind of have a specialization of different behaviors. There's also a muscle that crosses from the outside of your hip to the inside of your knee, which kind of lets you pick up your foot and like twist it towards the inside, lets you look at the bottom of your foot. So there's a very specialized muscle. And so you could potentially activate lots of other muscles to get the same behavior, or you could activate one muscle to get this very specialized behavior. So this is an advantage for getting specific behaviors. However, it is also generally a disadvantage for control systems and engineered systems, because you end up having too many choices. How do you decide which muscles to use and coordinate for any specific task, right? So if you have two muscles that control kind of the elbow flexion, right? You could activate just one of them all the way to get it to move like this. You could activate both of them partially to get the same amount of force, or activate the other one all the way, or any level in between. So you end up having an infinite number of choices in order to get the same behavior. So another advantage of muscles is that they are compliant. So here is a robot that uses artificial muscles. So they're not exactly the same, but they have a lot of similar properties, including compliance. And so this compliance allows the system to be pushed on, right? This robot is getting poked and prodded, and you see that it kind of is stable and automatically adjusts its posture in response to the pushing. So there's no controller in that robot there. It is just automatically adapting to the perturbations. So that is awesome, but for being a pain, if you're actually trying to control muscles exactly, it can be very difficult. When you tell it to do something, it might get something a little bit different out of your response, right? If you want to go to a very specific joint angle and you're compliant and something pushes on your arm, then you're not actually going to get to that joint angle. So what are some insights for smart cities in this? And so my insights from looking at muscles and understanding muscles behavior is that one, specialization allows for more efficient behavior. You can specialize specific areas of your smart city to really target specific things that you want done. I think that that would be a very smart approach in building a smart city. Rather than trying to be very general for everything, having some specialization will enable more efficient capabilities. In addition, or almost in contrast with that though, you need redundancy. And so in addition to kind of the specialization, it also provides a high level of redundancy throughout your skeletal system to have all these muscles. And so if a single muscle gets injured, then other muscles can take on its role and you don't lose complete functionality of your system. And then the last point is that compliance enables adaptation to the environment without control. And so this is very good because environments are very noisy and variable, and muscles allow adaptation without needing any control from the brain, right? So the system is able to adapt to small perturbations, problems, or anything that occurs without needing a decision from your brain in order to handle it. So having in your smart city, when your systems that interact with the environment or with people really need some level of compliance, not specific rigidity and specific set of rules that have to be followed, but really some amount of compliance for flexibility in situations. So let's go on to the next topic. Let's talk about local circuits and sensory feedback. So I'm bringing these together because they're really not separable. Sensory feedback and local circuits are intricately connected in how they control locomotion. And so we really need to look at them together. So what do we know about the neural system that controls walking? So here is kind of a diagram of things that we know or have very good hypotheses about how our nervous system is connected for walking. And so the nervous system is primarily made up of neurons. And so here, you'll get, I think, maybe the only equations in my talk here. So just how you have a general understanding of how the nervous system is working. So my models of the nervous system primarily have groups of neurons with similar behavior grouped into a single node that I call a neuron. This is kind of like a population of neurons that get similar inputs from other part of the nervous system or sensory system. And this neuron is a dynamic system. So it responds to its inputs in a dynamic fashion, which means it's not like a direct input-output response, but for example, the neuron could be slow to respond to inputs. So it needs lots of inputs over time before it becomes more active. Or it could have its own internal behavior that allows it to become active and inactive all by itself. So these are kind of dynamic neuron models that of your nervous system. And so here, people were very correct earlier in talking about electrical signals in the nervous system. So neurons primarily communicate via electrical signals. So the voltage of a neuron is basically the coding of a neuron, how active it is. And so the voltage describes that. So here we have the voltage of neuron 1 is described by this equation. And so neurons transmit information via synapses to each other. So as the voltage in neuron 1 goes up, then it injects current into neuron 2. And this current, and it will inject more and more current. And this could be a positive current, which makes neuron 2's voltage go up, or it could be a negative current, which makes neuron 2's voltage go down. And so this is how neurons communicate throughout the nervous system. And neurons are not randomly or fully connected together in your nervous system. Instead, they are arranged functionally to achieve specific behavior outcomes. So you don't have, over here is an example of kind of a general machine learning network, like the networks that Google uses, networks that are taught in machine learning classes. And this is really not how the nervous system is arranged at all, especially in the spinal cord level. There might be some evidence of similarities for this in the brain, but not in the lower level circuits. Instead, things are arranged much more functionally, and all the neurons have basically very specific roles, and often roles that we can point to and describe kind of in a wordy manner more than a mathematical manner. So for example, here is the control network for like a single leg in a cockroach. So we see we have kind of some repeated networks throughout the system for each joint. We've got connections, and we don't have connections everywhere. right? We have very specific connections onto very specific neurons. And some neurons are more connected than others. And things are still, there are lots of connections, right, in this network, but it is very far from a fully connected network. Or even, and you can tell that it's not randomly connected. There is structure in what is going on here. And so that control network coordinates, can coordinate all the muscles in a leg to create forward walking, right? So everything is very functional and has a purpose. So this is some work by my collaborators, Nick Szczynski, my previous advisor, Roger Quinn, and a student, Scott Rubio. You'll see Nick come up again later in the talk. So let's break down this walking control network a little bit more and understand how it works. So this network is composed of central pattern generator, sensory feedback, motor neurons, and interneurons. So let's talk about these. And central pattern generators are a set of neurons that go through active and inactive phases without external input, which means that they, kind of in an engineering standpoint, you have an oscillator network, right? So it just goes through multiple phases, oscillating, and does not need input from the brain in order to do this. So they're in your spinal cord, they do this. This is also what controls your breathing, for example. And so here, get this to play, we have kind of a CPG network that is driving an arm joint back and forth. So here is it's just two neurons, and this arm joint is driven back and forth by two neurons that then activate the motor neurons. Sensory feedback in this network is used to reshape the CPG behavior and period. And this enables the circuit to adapt to its surroundings. So here we see a CPG without feedback, and we see very regular rhythms in it. And if we add sensory feedback into the system, we see we still have our repeating rhythms, but they have very different shape now. And so and the timing is different. So timing and shape are both affected by sensory feedback in your legs. So here, there's sensory feedback that affects one of the neurons in this CPG. And we'll see that it basically speeds up the CPG when it's on one side. So we see that it spends far less time down here now and more time up here. So this sensory feedback is saying, hey, we've already gotten to the end. Let's turn around and go the other way sooner, rather than waiting for the CPG to just respond in its normal behavior. It is speeding it up. We know that the motor neurons are activating the muscles. So in our simulations, we see these motor neurons activating muscles in each leg. So I'll show you a couple models coming up. And so there's basically 6 muscles on the legs of these models. And so we have 3 of these networks causing the joint in the leg to go from extension to flexion, back and forth, right? And the sensory feedback is coordinating the extension and flexion between the different joints in order to enable coordinated walking. So here, we've also got kind of a higher level CPG that affects these CPGs that help coordinate the entire leg together, right? So you got each joint having its own oscillator network. Like here, we've got the hip. Here, we actually have the ankle and knee combined together. I won't dive into that too much right now. And we've got this one rhythm generator for the leg. So the leg is kind of coordinating all the lower level CPGs, and sensory feedback is coming into those and coming into the leg to help with all the timing. And so if we put these all together, use some engineering training skills, some optimization, we can see that we can get coordinated walking from a very decentralized system. Excuse me. So there is no brain that causes normal walking. Instead, it is a bunch of independent neural nodes in your spinal cord that are able to produce coordinated walking like this. And it relies on the sensory feedback in order to stay coordinated. So with this model, we can start to ask things like, how is this organization useful? So we can take the model, or kind of a more simplified look of that model, and perturb it. So in this model, we perturb the walking at 2 seconds. You can kind of see that things happen. The legs go from hopping to slightly different. Have to run again. It's not giving me control. So we can watch that again. Boy, yeah. So here you see that perturbation. Legs get out of sync and then get back in sync with each other. So how does this organization let that happen? So immediately after the perturbation, we see that the legs behave differently as it adapts. So because things are very non-centralized, and we see that each of the legs responds differently when this perturbation happens, and they're both able to coordinate their activity and maintain that kind of hopping motion without any high-level control of the system. However, because we've got one node that is a little bit higher than all the rest, that is kind of continuing to influence the system, so that was our high-level rhythm generator CPG, we see that our original timing is recovered and maintained in the system. So that means that there still needs to be kind of this higher level part ensures that gait is maintained. So, we don't have a whole lot of gaits in humans, but if we look at four-legged animals, they go through a lot of different gaits, right? Like walking, trotting, galloping, bounding, pronking, all sorts of different gaits. And so some system needs to kind of keep track of what the gait needs to look like and talk to all the lower level systems. But all the lower level systems still need to be capable of responding to perturbations, like maybe differences if you're kind of walking on uneven ground, right? The sensory feedback allows you to adapt to the unevenness in the ground on a very local level without requiring that high level control. But you need, we can have this kind of higher level network that kind of keeps track of what everything should be doing, and kind of what it's doing is kind of poking at everything, all the other lower level networks, and being like, hey, you should be stepping now, but maybe the sensory feedback is saying, no, not quite yet. But eventually they work together to get the system back to its normal gait. So some insights that I've thought of for smart cities with this is that the local adaptability and autonomy is a must. You must be able to respond to the local environment and the needs of the local environment, and to be able to do that quickly without having to send all your sensory information up to a centralized brain, wait for a decision from that brain to come back down on what you're supposed to do. You really need that local adaptability and autonomy in order to be responsive to the changing environment. However, these local components also must be able to communicate with each other in order to kind of maintain a more system level behavior, right? Or having kind of local level nodes that allow more influences. And so this kind of cross communication allows your systems to respond and adapt together. Right, so for example, in the case of walking, if the foot senses that the ground is a little bit further away, and so stance phase of your leg should be delayed, then a sensory signal will need to relay that information to all the joints in the leg, right? Not just you know, your ankle, which is close to your foot, that might notice that it's not touching the ground yet, right? So all the components that are working together need to kind of get this information so that they can all respond accordingly. All right, so that was muscles and local circuits and sensory feedback. So let's talk about the brain and then how this works with it. So honestly, I don't know a lot about the brain. I mostly study and model the local circuits. I'm starting to get into understanding this, the brain circuits a little bit more, and I would like to use a colleague's work to tell you more about how the brain influences local networks. So my buddy Nick Szczynski, who's currently at Case Western Reserve University, is starting soon at West Virginia University, has done a lot of the same type of work that I've just shown you, but not with mammals, but with insect systems. So here he is with his robot, praying mantis robot, and he used this robot for studying the brain impact on these local circuits. So the praying mantis is a great model for studying goal-directed behaviors because it is quite obvious what this praying mantis wants. We know exactly what it wants, and so we can see what its behaviors are. We can watch it track this cockroach, hunt it down, and then grab it. So it is very clear what this praying mantis is trying to do, and so we can start to investigate how what the brain wants ends up at different behaviors at the legs. So here we see this whole leg network again. It's for a praying mantis and not a cockroach this time. And it's simplified down to 4 joints and a little bit neater. So let's go ahead and focus in on one of these joints and look at how it interacts with the high-level control. So here we can see neurons with easily identifiable names like tracking, pursuing, forward displacement, head direction. And so these would be like decision makers in the brain that have decided what to do. And these decisions are going to affect the local circuits. And instead of taking direct control of all the muscles, it really only needs to modify the control of the lower level. So we see that these neurons only have a couple of connections down into our low level control network. So this is our low level control network with CPGs affecting motor neurons and controlling our model. And so we see that these high level decisions are really filtered and only have small influences on this network. And these small influences can result in more dynamic behavior changes. So that's what I just said. So let's go ahead and watch it. So we've got this praying mantis robot. It is looking, it's got some, for its eyes, it's got photovoltaic sensors. And so to the eyes like that, a light source is food. So we'll see, sorry about that. We'll see this food move around, and the head will track that. And it's only going to be sending, we saw small control signals down towards the leg, but we'll see that the whole leg changes, the foot motion changes as it moves around. So here we'll see some traces of like a normal forward step, but as this light source moves to its left, we see that the foot reaches out towards it and pulls backwards instead of just kind of front to back on itself. And then as it moves the other way, we see the foot again kind of moves towards the light and pushes away from the robot. So it goes from, it's actually very different joint behaviors where it pulls in to pushing away, right? And so different directions of the joint, not just different magnitudes of how the joints are controlled, but even different directions for different joints. So, yeah, so some insights for brilliant cities is that you still need a central controller. It is best utilized to do hard processing and provide direction and influence to local circuits to help them keep on track and maintain coordination with other local circuits, right? So you still need your brain. The local circuits are very powerful in the things that they can do, but the brain is still very important. And then another aspect that I guess I didn't really show you evidence for, but brains also do not get all the sensory information. So that sensory information comes into the local circuits, it gets filtered, processed into more important aspects that are then get sent to the brain. And so in a grant that we just got funded, this is one of the things that we are going to be investigating more is what type of information the brain needs in order to make relevant decisions. And also investigating a little bit more of how the brain influences the local circuits. So, and then one more insight that we didn't really dive down into, and this is one of my biology collaborators' favorite compare and contrast for thinking about biology versus engineering is understanding how noise affects the system. And so in an engineered device, when you design, manufacture, and control them, you're trying to do this in order to eliminate variability. Variability is regarded as noise. It is unwanted. But in biological systems, this variability is not noise. It is the signal which enables better control, better adaptability. It is what drives evolution and development and learning as well. So when you have a very noisy system, which a city is going to be, it is maybe not best to try and design everything in order to eliminate the noise, but instead to take all that variability and use it as signals that enable better adaptability, better learning, and better creativity moving forwards. So that is the end of my talk. Thank you very much. I'd like to thank a lot of my collaborators, like at the University of Vienna, Martin Fischer, Manuel Schmidt, Manuel Andrada. There's also Dirk Arnold and Julia Bilde, which are not on here. And then Case Western, where I did my PhD, Roger Quinn, Nick Shazinski are two of my main collaborators. And yeah, so we've got time for questions, I think.
Thanks, Alex, for your presentation. If you have any question, you can use the chat, or you can raise your hand. I can unmute you. So I see there is a question from Jill. So go ahead and ask your question, Jill. I just unmute you.
I have 5 questions. The first one is, would you classify the human body as over-engineered?
No, it is not engineered at all.
The second question is, how did so much redundancy come about during the evolution of the human body?
Yeah, so in one of my earlier slides, I put redundancy in quotes. I think that there is very little to no redundancy. Instead, you have more specialization and more adaptability, adaptable capabilities. So even if you have multiple muscles over one joint, those different muscles will not be exactly the same, and they're not connected exactly the same. And so they have different capabilities. And so, yeah, I would not call it redundancy, although often it is called that. I think it is much more important than that.
The third question is, do you expect that the human body will eventually evolve to become more streamlined in order to reduce unnecessary redundancy?
No.
And the fourth question is, do you think that most technology problems would benefit from being modeled as behaving as biological systems?
That's an interesting question or thought. I think it really depends on the system. I think that a lot of engineered things are built to eliminate variability, and this can be generally good for many things, like manufacturing, right? If you want to make 10,000 cars, you probably don't want them all to be very different from each other. That would not be a very efficient way to build a ton of cars or a ton of buildings. And so it's certainly not always in your interest to want variability in systems, but I think many systems inherently have a lot of variability and especially when we're looking in the context of smart cities, right? Every city is going to be different, and you have lots of biological systems interacting within a smart city. So I think whenever you are working within the context of a lot of these biological behaviors, you need to kind of keep all of this understanding in mind as you design and build things.
My last question is, I didn't quite understand what you said for your final point. Were you saying to learn from the noise rather than trying to eliminate it?
Yes. Yeah. That noise is a signal, and it can be a signal of importance versus something that you need to get rid of, right? Especially, I think, in a human society where we want to continue to encourage creativity and freedom of expression and all these things, that engineering our systems, we want them to be adaptable to that versus instead squashing that all into very specific mechanisms.
Alex, I have a question, and if it's too meta, I apologize from the get-go. But listening to your talk, it has occurred to me that you're describing biological systems and cities as something that inherently has emergent behavior. All these little things act together, and then a behavior emerges, and there isn't this central control that says this is how this has to happen exactly. And our entire engineering tradition and engineering education is really built on this idea of we're designing systems that are reliable and plannable and do exactly what we tell them, and they're not supposed to do anything that we didn't design into this. And we really force students to get out of the uncertainty mindset. Uncertainty is bad, then you didn't do the calculation right. If we want to tackle technical challenges in smart cities, as you described them, do we need a different type of engineering education?
That is it's a good question. So I think that we could probably expand that engineering education because there will always be a high level of uncertainty, and I think that we need to get maybe a little bit out from the idea of controlling the city, as in, and more towards enabling the city to produce its best behavior. If that makes sense.
Thank you.
Yeah. I've got a question from Chip. So,
I think he's raising his hand. I can unmute him. Yeah. Go
Okay.
ahead, Chip, if you ask.
Right. So thanks very much for the presentation there, Dr. Hunt. That was really nice. The question I had, if indeed these low-level circuits, the neurons, are reacting to the environment quickly and efficiently at some level below the central control, could we design a fully distributed electrical grid, like with Tesla tiles on the top of your house, so that we could provide efficient local power sharing in a similar fashion? And thus, could we then eliminate a central distribution system?
I think that there is general merit in that idea, that there can be a lot of decentralized things on the electrical grid. I once briefly played around with a model in which I did produce I think it was a control of pull from windmills into a grid in a very decentralized standpoint, with that it enabled balancing of power in the grid. So I think that that can be done on a very decentralized capability, and it still needed like a central kind of hub to tell the entire, that kind of influenced all the nodes. And so it still kind of required general communication, but the nodes were able to kind of respond more directly to an individual wind turbines changes and maybe power capabilities, and kind of balance the overall load in the network. So I think there's merit and there's possibilities, and I think it's worth researching.
Okay, we have another question from Dr. Daniel. Go ahead, Dr. Daniel.
Hi, I have been involved in artificial intelligence for a very long time. And in the old days, we used to make a difference between artificial intelligence, which was trying to imitate the human, versus mechanical intelligence, which was just trying to make computers smarter. And the main reason why I thought that trying to imitate human was a loss of time is that the brain has zillions of neurons, while computers have a few. So my question is, in the motion system, just for the praying mantis, how many neurons are we talking about?
In our model here, what do we got? Maybe about 20 per joint for joints, 80, and then maybe about 90 per leg. And then you've got 6 legs. So, yeah, maybe in the order of around 500 to 600 neurons for kind of control of various different aspects, basically allowing for tracking of prey and walking forward in a few ways. So.
Okay. If Dr. Daniel, he finished. There's another question from the student. They asking for student where they can, where could student learn about more about neuroscience at Portland State? Do you have a specific courses that you recommend, or?
You say neuroscience at Portland State?
Yes.
Okay. Dr. Radhika Reddy teaches a few neuroscience courses. There's a sensory neurophysiology and kind of a general neurophysiology course. And then this past term, I created a course on neuromechanical modeling. And so I'll probably be offering that either once a year or every other year.
Okay, any other questions? You can ask through the chat, or you can raise your hand if you have any other questions. I don't see any other question, Dr. Yetter.
Yeah, and we are approaching bonus time anyway.
Yeah.
So thank you so much, Alex, for a wonderful presentation. Really, really appreciate it. We will post your slides with your permission on the D2L side. And we also have a hidden YouTube channel for all the talks in this series so that people can access the presentation. So thank you very much. Thank you to everybody and a happy weekend. Thanks.
Mhm.
Thanks,
Thank you
Alex.
all.